Welcome back to ECE 442-542. You have 1 week to get ready for the final. If you aren't ready now, or you have a week to remember, if you have it all stored up, our final is next Thursday, a week from tomorrow, from 1 to 3 p.m., and it will be in this room where we are located right now. If you are working on 542, if you are carrying your project around, it needs to be completed by this evening. And also the teacher course evaluations, which right now are hovering under 50%. I would like to see those improve. If you get them up to 80, maybe something good will happen. Just saying. Homework number 8, if you want some extra credit, you can receive that by turning that in or submitting that in by tomorrow, and the time is always at 11:59 p.m. The office hours after today, we have a few more, and obviously the top 3 have been modified slightly from what they normally are. Mondays will go a couple of hours instead of 1 hour since we don't meet as a class on Monday. Friday, it's shifted. It's 1 hour from 10 to 11. Tuesday, which we normally don't have office hours, is 12:30 to 2:30. And Wednesday is also 12:30 to 2:30. And you can take advantage of those. If those do not work with your schedule, let me know, and maybe we can work something else out. Today we have a long list of goals. One is to inform you about the final exam. The other is to talk about these A through, how far did I go alphabetically? F on different block diagrams of a state space representation. And it's really it's a visual way to sort of interpret the equations. Instead of me just writing down equations that go through these open loop, full state feedback with a reference input, estimator, full state feedback with integral control, estimator with feedback. I think it's more intuitive to look at it graphically from a block diagram perspective, and we'll try to look at that, and we will actually figure out where to go in terms of if you're now directing this system to go somewhere. That's part of homework number 8, and it probably might be on the final exam, hint, hint, but knowing how to incorporate non-zero reference input might be important. And then the others we'll look at via a block diagram, and we'll look at how we might implement integral control with full state feedback. We were using integral control in transfer function based controllers in the PI, the PID, that I was the integral. We'll look at how we might incorporate that with state space descriptions in a block diagram, and then how do you sort of go back and forth between block diagram and equations, time domain, writing the formulas based on just a block diagram description. That might also be important for final exam. Maybe not so much in this context, but in general. How do you go between a block diagram and a time domain difference equation, transfer function, etc.? And then the other 2 are, what can you do if all you really have available would be the output measurement and the input? The others are assuming that you have full access to the entire state vector. What if that's not true? Then we start looking at E and F, where we're only measuring or have access to the output waveform or signals and the input. Can we use those to actually estimate the full state vector? And if we now have a way of estimating the full state vector, can we actually sort of fool the system and use that as if it was the full state vector? And that's what the last one is. is we estimate the full state and then we apply the full state feedback gain that we derived maybe earlier when we were dealing with the regulator design. And it all sort of fits together. As I said, we will look at the integral control in more detail, looking at the equations, and then with time, I think we have plenty of time since I don't believe there's a class after this, so we can go until 10 or 11 tonight probably. We can talk about full state estimator and a full order compensator, but the compensator is combining the full order estimator with feedback. And if we look at that block diagram properly or in the right way, we can actually see that we could interpret a transfer function idea from that realization of a control law. Probably what you're more interested in right now is final exam. What do I need to know for the final? The final will be comprehensive. It will be 15 questions, and before you start getting too nervous, a lot of our midterms have been 7 or 8 questions because they have multiple parts to them. So don't get too hung up on the 15. These 15 will only have 5 parts each for 75. No. They won't be broken down into multiple parts. You'll really probably just have one question being asked. It might have a few steps, but it really is not going to have multiple parts associated with each question. And because the later material depends on the earlier material in the semester, that's why the exam could be considered comprehensive, but we may just focus on some of the earlier material through those 15 questions. But I joke sometimes, and you don't feel like you don't consider it much of a joke, but I could say I could give you one question, and it depends on everything throughout the semester, and if I formulated it right, I wouldn't have to grade much. I could make the very first step very difficult, then you wouldn't get it, and I'd go, well, they can't answer it. No. So that's the intent of giving you multiple problems, so that you can, if one of them does seem to throw you off, I would just move on. It probably will come to you as you're working through some of the other material. Process is similar to what we've seen before. You'll have now 4 sheets of notes, so 8 pages of material that you can create. You can bring in your favorite Z-transform tables and whatever implements you like to bring with you. Protractor, compass, ruler, straight edge. Just make sure you don't harm your neighbor if you have a divider or something like that that you're measuring distances with, which you might want to measure distances for what? Maybe settling time, if you want to know what is the exact radius from the origin to that particular pole, dominant pole. You can have a calculator, just don't make it a computer, although they are sort of a computer. But no class notes, no books, no neighbor, no phone, no computer. Those are the no's. Questions on the process for the final? Yes?
You said that the later material depends on the earlier material. Does that mean it'll focus mostly on everything since the last exam? Or will we have questions in the structure of what we see before?
The question was, am I going to focus my exam questions on later material? Not necessarily. I will try to uniformly distribute those throughout the semester, but you can anticipate a few state space type questions, and that's the later material. I'm thinking I will try to go in, lock myself into a room maybe and record some review material. I haven't yet decided. I don't know that you'll want to come and listen to me do that. So that way I don't have to worry about other people's schedule. I can just kind of go in a closet and lecture. It's real fun that way to just stare at a wall, but I've done it before. And So look for that maybe, but you already have the final exam on the syllabus. There is a list of about 23 topics or skills, pieces of knowledge that you should know. That should probably prepare you nicely for the 15 questions on the final exam. Other questions about the final? That was not a question. I don't know if you caught that on the mic. Somebody said make it easy. And I don't like to talk about easy and hard, because if I say it's easy and you start thinking it's hard, you go, wow, if this is easy, I don't even want to look at problem 2. So I don't like to set you up for the wrong feeling. State space design. We're going to go through some block diagrams now. And really I want you to just get comfortable with seeing the block diagrams, being able to translate those into equations. And obviously these will be available to you as notes, as always. But here is the state space representation. Again, this delay is a generic bank of delay blocks depending on the size of your state vector x. Here we have x being n components tall, the state vector, and phi, the system matrix, is always square. It's n by n. Gamma, the input matrix, is n by m, Michigan columns wide. And the output matrix H is compatible with the number of output signals that you have available or that you're calling outputs, and that we have Q of those. And for whatever reason in this block diagram I went ahead and included J, a matrix J, which is the direct feed-through connection from the input U directly into the output Y, and you can see that there's no delay in that connection from U to Y, and that you can see actually in the output equation. But the output equation is linear. If you needed to Z-transform that, there's no delay in the output equation. That's a very straightforward Z-transform. You just have to hit the shift key or capitalize the output. The dynamics, you have to really just worry about the left-hand side. So how do we know that it's open loop? And maybe that's a little bit unclear from the diagram, but that phi looks like there's a feedback. But that phi in this case is really just consisting of the system itself, the way that it feeds into and defines or creates the next set of dynamics. So in this case, open loop means I'm not explicitly going in and measuring X and feeding that back, or measuring Y and feeding that back. I am obviously showing some interconnections between the state variables and the next set of state variables, but that's phi, that's how the system is dynamically defined. That's the system matrix. And I'm just saying this is open loop relative to what we'll get in the next few block diagrams, where we start going in and physically measuring some of those signals and feeding those back to do what? To change the dynamics. We may not be happy with phi. In this particular system, if I gave you that block diagram and I said, how does this system behave? What would you do? If you had access to gamma, J, H, and phi, and I said, how does this system behave? What would you be looking at or doing in response to that question? Is that question vague enough? What would you be looking at or thinking about if I said, how does this system behave? Settling time. So now you're thinking, okay, how do I determine what kind of performance specifications this system exhibits is sort of what you're suggesting by settling time, but how do you determine that? Poles, or you could walk up and kick it, couldn't you? Shouldn't kick that, it might damage my equipment, but I can kick this. So you shake it, but how do you sort of shake it? You could find the poles, which are the eigenvalues of phi. The modes, the way this system moves when it's kicked, is determined by phi in the open loop, because you're not changing the dynamic behavior. This is just how the system behaves. We probably have bets on how many times I'm going to kick something. I'm guessing maybe that's what it is. Somebody just won a bet. I can take that money to the hospital with me when I get my ankle repaired. Huh? Here are the equations. If you actually z-transformed those relationships, that little x of n plus 1 becomes z. That's the advance operator. And here I've gone ahead and introduced an identity matrix so that I can actually factor out or combine the pieces in that equation that contain the state vector z-transform capital X of z. And this then, in red, is the open loop transfer function. And if you actually did the mechanics of finding the inverse of zi minus phi, what's in the denominator is actually the determinant of zi minus phi. And the determinant of zi minus phi are the values of z that cause that to vanish, and those are the poles of your system, the open loop poles. That's the first block diagram. That's just really one way to visually see those difference equations that model the system. If we weren't happy with the modes in phi, we could change those by going in and measuring the state vector x, scaling each of those with some constant, and creating the input u that drives the system by saying, oh, that's minus k times the state vector x. And this is now talking about behavior. I don't want to scare anyone today, but the last time we were sort of trying to make this, drive this point home, this is when we say behave to the system. We tell the system to behave. That means that we're picking on or trying to design k. We're not telling it where to go. We're just telling it to behave, because you can see here there's no reference input that's telling the system where to go. And again, that's the closed loop system, because I've now tried to indicate that with the blue. I'm physically going in and saying I have the ability to go in and access the full state vector. If that's 10 different elements, I can measure each of those, scale those through the gain matrix K, and use that to change the dynamic behavior of my system. This is, well, the B is part of homework 8. Here is definitely homework 8, where we want to actually use a reference input when we tell the system where to go. So not only do we say behave, but we say go to your room or go somewhere. So I'm doing that so that you get a feel for, if somebody's kind of acting up, you say behave. You now know, oh, they need to change their behavior. Well, that's with K. And if you tell them where to go, that's when you have an external reference input or an N sub 1 matrix. And if we put that now into this block diagram, I've tried to color code it a little bit. Not only do we say behave with K, but now we say here's where you can go. If we want to command the system to go to 10, then we want to select n sub 1 in such a way that the transfer function from the input r all the way over to y has what kind of property? If we looked at the transfer function between r, the reference input, and the output y, and we wanted to be able to track a constant input at r with the output y, what would we want? What kind of property would we want in that system? We would want a DC gain of 1. You can now, from this block diagram, determine what the equations are that govern the behavior of that system, its transfer function, and you could then try to find what value n sub 1 will give me a DC gain of 1. Then I would have, if you knew everything perfectly, if you knew phi without any errors, if you knew gamma without any errors, and if you knew h without any errors, then you could pick k and n1 to give you very nice tracking due to constants. So let's see if we can walk through that, because this is really sort of what you're wanting to do on homework number 8. You should be able to write the equations that govern this system's dynamics. We have x at time L plus 1. We're now looking at the output of that summing junction, and that then is a function of the input signals to that. So one of those input signals is simply phi, x of L, and the other one is now, let's say, plus gamma, and now we slide back and we say what makes up u of L. It's really gamma u of L, but let's now go ahead and insert what u of L is equal to, which is, and we can write it maybe from 6 o'clock to 9 o'clock, going around in clockwise fashion. We can say that u is actually minus k x of L plus n sub 1 r of L. Everyone sees where that comes from based on the block diagram, I hope. And if I give you a block diagram, how could I change this block diagram that might throw a curveball to you in a week? How could I change this up that might be a little different? I might actually go ahead and be more explicit with those delays. I might expand that and not explicitly show phi. I might show all of these different interconnections with the different delay blocks. So the delay and all of the elements in phi are there staring at you, and they're not collected nicely or neatly into a matrix phi. But you could put them that way if you wanted to. You could start labeling the outputs of your delay blocks as state variables, and now you can, if you wanted to, define phi in that way. But hopefully this expression is clear where that comes from. Let's now group some of the common terms. We have the state vector x on the right-hand side. We can put those together. And just distribute gamma across those two terms in the last part of the right-hand side. And if we wanted to now determine what the behavior of this system was, now it is a closed loop behavior, we could now look at the eigenvalues of phi sub c. How have we changed the behavior? If we said behave, now you would have to decide what you wanted that behavior to be. And if you wanted a certain set of dominant poles, you could pick those two based on performance specifications, percent overshoot, settling time, peak time, and maybe put the others inside that in terms of concentric circles so that the two still dominate. And an easy place to put those is at the origin. Those are as fast as you can get. Now, hopefully you can see that we can Z-transform this and plug it into the output equation to actually find y of z. And now I don't up here have this direct feed-through connection from the input u over to the output h. J is 0. And so now I have h times zi minus phi sub c. So I'm consolidating or replacing phi minus gamma k with just this one matrix, capital Phi sub c, inverse gamma n sub 1 r of z. And if this is a little bit too big of a step, you can put in the intermediate line to illustrate, oh, z transform the output equation, and now replace capital X of z in the output equation with what I could find from the z transform of that dynamic equation. Here, is our closed loop transfer function. Or if you didn't want to see all of that collapsed down inside capital Phi sub c of z, you could say zi minus phi minus gamma k inverse gamma n sub 1 r of z. And now this is exactly the same t sub c of z. It's just now I've written out what phi sub c is actually equal to. Or now y of z can be more compactly written as just a transfer function t sub c and the reference input r of z. Again, if we've already changed the behavior of our system with k, maybe the only thing that's left to be determined is this unknown matrix n sub 1, and if we have a single input, single output system, that matrix n sub 1 is actually 1 by 1. It's really just a scalar. And what we want to do then for homework and maybe the final is to select this matrix n sub 1 to create a DC gain of 1 between the reference input R of Z and the output Y of Z. And T sub C of Z is just H, Zi minus phi sub C inverse gamma n sub 1. And if we want the DC gain to be 1, what does that mean for this expression? Or how could we now find n sub 1 if we want the DC gain of this to equal 1? Now we're looking at the limit as z goes to 1, right? That's DC behavior in the z-plane. We simply replace z with 1. That's pretty easy. Now we just have the identity matrix. And we look at what? Setting T sub C of Z equal to 1 and solving for N sub 1. We want that to equal 1, and so now we're looking at H, I minus phi sub C inverse gamma N sub 1, or if we solve that now for N sub 1, let's assume that we have a single input, single output system. H is one row tall, and gamma is one column wide. That mess, H times I minus phi sub C inverse gamma, is a scalar. It's 1 by 1, even if the matrix phi sub C was 10 by 10. We would have to invert it, that 10 by 10 matrix, but it would all collapse down when it was pre-multiplied by H and post-multiplied by gamma to give us a scalar. Or N1 now becomes 1 over H I minus phi sub C inverse gamma, where this expression in parentheses is scalar for a single input, single output system. And that's what you'll want to examine on homework number 8, is can I now solve for N sub 1 if I want a DC gain of 1? Yes?
And you wouldn't be able to move that, the inverse up into the top of the fraction with the inverse?
So now, no, the question was you want to move that inverse up into the top of the fraction. We can't do that because now this is possibly a matrix. So if that inverse was a scalar, you could plop it up there, but now it's actually a matrix, and so we can't be as cavalier with our shuffling of operations, matrix operations. We now have to perform this I minus phi sub C inverse on whatever matrix dimension we have. It's 5 by 5, it's 2 by 2. You should be able to invert a 2 by 2 matrix. And then it will collapse down into a 1 by 1 scalar when you hit it on the left with H and on the right with gamma. Because H will be a 1 by 2 times a 2 by 2. That gives you a 1 by 2. Hit a 1 by 2 by a 2 by 1, and you get a 1 by 1, a scalar. Questions on that? And I think on the homework, I actually have you compare maybe with a DC gain of 1, and maybe I say, oh, just let N sub 1 be 1. Say you don't want to do all of this. Then compare the results, and hopefully you will see that when you don't judiciously select N sub 1, you may have an error between where you want the system to go. Maybe you tell the system to go to 10, and it actually goes to 8. Now you have a steady state error. Here, if you know everything about the system, you know the phi, the gamma, the H, etc., you can select N sub 1 carefully to give you, I want a 10. If I put in a constant 10 at the output, it's going to be there. Questions on that example? So that you need to know for the final and homework number 8. You don't have to work homework 8 if you don't want to, but you need to know it for the final. Now, I kept emphasizing the fact that, oh, you could pick N sub 1 and make your DC, or make your steady state error 0 if you knew all of these parameters precisely. What do you do if you don't know them precisely? Now maybe what you want to do is introduce an integrator. And this integrator will now compensate for maybe some uncertainties in your parameter values. As long as the closed loop system stays stable, you can now track a reference input with 0 error, even if there is some uncertainty or variation between where you thought phi was and what those parameters actually are. Here's the block diagram for that. The black, most of the black here is the original system that just governs the open loop behavior. We changed the system's behavior with, and now this is not our original K, this is K hat, because I've actually introduced some more dynamics via this integrator. The integrator I've tried to incorporate in the red. So you know an integrator in the analog setting is a pole at the origin. Well, a pole at the origin corresponds to a pole where in the z-plane? At 1. And this integrator piece has a pole at z equal to 1. The z to the minus 1 block is actually a bank of z to the minus 1 blocks in general. It depends on the dimension of phi. But if you know now you wanted an integrator, you could say, oh, I can build an integrator in a block diagram. That's just 1 over z minus 1. And I'm going to gain that up with a gain parameter k sub I. And what do I feed into that integrator? Well, that's the output of this summing junction, which is the difference between where I am with my output y and where I wanted my output to go, the reference. That's y minus r. So I'm taking that air signal and integrating it, and then using that to help drive some of the input of my plant. The input of my plant is not only an integrator, but it's also a feedback of all of the state variables x. And if I wanted to, I can, based on this block diagram, simply write down what the control signal looks like. What is u in the time domain? Little u of L is now just made up of 2 pieces. Those pieces are a little bit different from each other, but what do you know has to happen if you write down this equation and you say u of L is equal to, and u of L, let's say, is 1 input. What do you know has to happen on the right-hand side of that equation? If u of L is a single input, what do you know u of L is as far as it's a scalar. It's a matrix that's 1 by 1. Well, if this equation is true, then everything on the right needs to be a scalar. It needs to be a 1 by 1 matrix when you end up performing the multiplication. And that now forces the dimensions on k hat, and it forces the dimensions on k sub I. If you had one integrator, then I simply have 1 x sub I, and k sub I is going to be a 1 by 1 matrix. But if I had 4 state variable components, a position, a velocity, a voltage, and a current, those were making up my 4 state vector components, what's the dimension of k hat? It's now 1 by 4. It's a row vector that's 1 row tall and 4 columns wide. And we will come back to this and start looking at what this actually might look like in the time domain. Or now can we rewrite this in what I will call an augmented state representation? Can I now build up my original state space representation? Can I augment that to incorporate this new state variable, little x sub I? So if my system matrix originally was Nevada by Nevada, if I have one integral state, my new system matrix in the augmented system will be Nevada plus 1 by Nevada plus 1. I will have grown that system matrix by 1 in the rows and columns. And we'll see that in just a minute. But before we get there, I wanted to talk about two more block diagrams. And these are now motivated by the assumption that we have been, or trying to eliminate the assumption that we've been using so far. So far we've assumed we had access to all of the state variables. What if we don't? We want to now estimate X by just measuring the output Y and the input U. We don't want to assume that we can go in and measure all of the state variables X of L. And how are we going to do that? How do we build a full order estimator? This is the system. That's the model of whatever it is that we are playing with. Maybe that's a DC motor. Maybe that's an airplane. Maybe that's a robot. It's now describing the dynamic behavior of the system that we are wanting to learn about. But all we can do with that system is measure the output Y and the input U. We can't go in and access all of the state variables. We want to be able to estimate those. But we're assuming we know phi, gamma, and H. And we want to build an estimator. How might we do that? If we know phi, if we know gamma, and we know H, what's to stop us from putting all of those into a computer, into a microcontroller, and basically trying to numerically generate this block diagram? Isn't that okay? Can't we just copy this? There's no IP protection, so we can actually copy this. Well, all right, I see some blank looks, so let me just go ahead and show you that I'm going to copy this. I'm going to lasso this and copy. Okay, now what? Well, now what I want to do is actually duplicate that here. Let me do it here. And now, what if I actually use the same input here as I have down there? If I connected the inputs U, if I know what I'm driving the real system with, which is up above, with what's down below, are the outputs going to be the same? So here, I've copied this, so I'm going to show the professor that I know that I'm copying, so I'm going to hat these. I'm going to put a party hat on those, since you're probably going to be, no, you're doing homework tonight, aren't you? So here are our hats. U is still the same. U is what we're injecting, but now we're assuming that these are hats. But is X hat the same as X? If I'm driving this system, I'm assuming I know perfectly gamma, phi, and H. Is Y hat equal to Y? Is X hat equal to X? If I did it right? If I copied it right? What did I do wrong? Looked like a fine copy to me. But what we don't know necessarily is who's gone up and kicked the real system and where those states are when we start to inject the input U. The top may be starting from a different configuration than the bottom in terms of variables. Oh, great. Now X sub 1 is at 3 and I'm at 0. Now what? How do I get rid of that difference? If all of my initial states X are maybe different than all of my X hats. How can I compare these two behaviors if I'm injecting the same signal U? What do I have available? I said I can't go in and measure X. I can go in and measure X hat because I built that in my computer or in my microprocessor or in my system. I've built the bottom out of my knowledge of the system. I now know there's maybe a difference between X and X hat. How do I maybe eliminate that difference? What do I have to work with? The U's, but the U's are the same. What else did I say I can use? USE. What do I have available to me? I know gamma, I know H, and I have phi, right? I fixed those. Those I'm not going to necessarily adjust because I'm assuming that there's no error in those. But I can measure Y, and Y hat I have because that's in my model, that's in my computer. Why can't I just now take and compare Y with Y hat? Meaning, what if I say Y of L minus Y hat of L? That's going to generate an error in the output. And now can I use that error to somehow change my estimate of the state? I'll say there's E sub Y of L. Y is K dimensional, and X hat is N dimensional. So I can't just feed that error directly into that summing junction. I have to make it compatible with X hat. So I need to scale that with a matrix. I'll just say L sub P. And there is now my estimator. I'm now going to select L sub P. This is now just a matrix, like the K. You know how to pick the K? Well, if you have a little bit more time, and we will, I guess, if we're going to midnight today, we'll figure out what equation we could use. It's the dual problem, but we could find a way to solve L sub P, similarly to how we've picked K. But now L sub P is just going to be selected to drive the speed with which X hat approaches X. How quickly can we sort of make X hat look like X? Our goal in this block diagram or in this full order estimator is we want X hat to go to X as the time index marches on, as it increases. And this will be done by selecting that gain, L sub P. And that could be called the estimator gain. Like we've had the full state feedback gain, now we have an estimator gain, L sub P. If we can select L sub P to make X hat look like X, now we can apply full state feedback. Even if we don't have access to X, we can say, oh, well, we kind of have a copy of it. We have X L hat. We have X hat of L. Let's use that in this full state feedback configuration, and that's our next block diagram, which is right here. You didn't know there were so many block diagrams, did you? But now I have, and they're black and blue. We're just completely black and blue with block diagrams. And red all over. The red is trying to show how we are estimating and feeding back in order to control that system. So now we've controlled the system with estimator feedback. This is now our full order estimator with estimator feedback. You know the nice thing about this? Really, there's something nice about this? Is that these design problems can be decoupled. You can design the K independent of the L sub P and then put them together, and they'll still behave the way that you want. But speaking of behavior, now we have the behavior of our system, which is K, but we also have the behavior of our estimator. How quickly does X hat go to X? So if we have two different behaviors and the system is really going to depend on a good X hat, which set of dynamics do you think we want to have be quicker or faster? The estimator dynamics or the system dynamics? That's a head scratcher. So what do we want to do? We're trying to do two things. We're trying to estimate the state X with X hat, and we want to use that estimate, X hat, to control the system. So there's two sets of dynamics. The estimator dynamics and the system dynamics, or the behavior of the system. Which do you think needs to be faster in quotes? Pardon? Did I hear an answer? No? Was that a yawn? Oh, a yawn. You don't admit that. I'm taking down names for extra credit for attending the lecture, right? But only if your eyes are open. Here you actually want your estimator dynamics to be faster than the control dynamics. You want to get X hat to X quicker so that you can use X hat like it was X. But all of that is sort of relative. You just have to play with it, just like you're playing with your project to get it to work. But just if somebody starts talking about estimator dynamics, control dynamics, you might remember, I don't know, Tharp was going on and on about something with respect to full order estimator and behavior and sending us to our room, telling us where to go. All of that can be incorporated. Here, do we have an external reference input? What's this system going to do? It's only going to behave as a regulator, isn't it? We can't tell this system where to go because we haven't injected an external reference input. This will just behave in response to some disturbed conditions on the state vector. But we could inject a reference input if we wanted to. Questions on behavior and where to go? I'll take my glasses off because I don't want to be told where to go. So we want to estimate X with X hat and control the system with that estimate. Or we're now using U of L is equal to minus K X hat. If I ask you the following, so now I'm just having fun. I'm always having fun, huh? And you guys are going, oh boy, I'd hate to be at his house. He considers that fun. All right, so what's the dimension on this combination? What's the dimension of this system? 1? Yes, well, no, it's two-dimensional, isn't it? It's not, no. So let's say that I have Nevada state variables, and let's say Nevada is 4. if Nevada is 4, if I have 4 state variables, that means X of L is a position, a velocity, a voltage, and a current. How big is this system's overall dynamics as designed? This full estimator with full state feedback, with estimator feedback. Anybody want to? I've already heard one answer. Actually, I've heard 2 answers. I've heard 1, I've heard 8. Any other answers? Pardon? Another yawn. We have a state vector 4, and what's our estimator's dimension? 4. So how many delay blocks do we have? We have 4 up above, we have 4 down below. If you drew that all out, and I said, what's the dimension of this block diagram, you would quickly start counting on your fingers the different delay blocks, right? And you would count 8. So this would be an 8th order system to control the original 4th order. That's the full order estimator. It's using 4 state variable estimates to try to control the system. Is this what? Is this what?
Is this lower than the full order estimator?
So is this lower than the full order estimator? Slower? I can't hear either. I can't see and I can't hear. So this one, this is the full order estimator. There's no control signal going back into U. Somebody's just injecting a U. Dimensionally, this is the same, isn't it? It's 8th order. But this has what kind of dynamics? Is this slower or faster than this set? And does that question even make sense? So this one, you have what? You have the estimator's dynamics in both. L sub p is influencing how quickly x hat goes to x. So that's in both, isn't it? But what's different? This one, which one do I show? This one, it has feedback. And what are you doing with K? Probably. It depends on what you use K for. You could use it to slow down the system, but typically we use K to speed up the response, don't we? So this would be faster because the other one just has the open loop dynamics of phi. So if we've used K to speed up the system, then this one would be faster, in quotes, than the other one. That's just the estimator with the open loop dynamics. See, we could just have fun all night. All these different questions. Fun is relative, isn't it? I had to put that in quotes. All right, so let's now look at this integral control as sort of a review for the final, in a way. Here is just incorporating an integrator into the system, into the controlled system. We're trying to change the dynamics with k hat, and we'll also influence the dynamic with the integral gain k sub I. We have 2 different gain or sets of gains in this system. We have the integral gain and we have the full state feedback gain. We want to know how can we maybe figure out how to design k hat and k sub I. How might we do that? And this is working from the block diagram. In order to implement this controller, in order to implement this full state integral control, we have to determine or find k sub I and k hat. So the plan is to put this into a representation that will allow us to use what we've already done. Can't we just find a k? Yes, that's what we're going to do, but we're going to have to build a bigger system. We're now going to augment the system because we now have one more delay block introduced by that integrator. Let's now figure out what that looks like, and this is what I'm saying is sort of the review for the final. If I gave you on the final that block 1 over z minus 1, and I said, can you give me a difference equation associated with that, I hope you would answer in the affirmative. Yes, I can. So now if we have this, let's look at the dynamics. Of the integral piece in that block diagram. If that's our transfer function, we need to label the input and the output so that we have some signals to play with. Let's now label the input as E, because sometimes that represents an error. In this case, it is an error between the output Y and the input that we're the reference input R, so calling it an E is appropriate. And we've already called the output of that the integral state. Let's just call it capital X sub I, because we're in the frequency domain. Now what do? We've now labeled it. We're looking to find a difference equation. What's another step in this process? If you were looking for extra credit, you would just do the following. Yes, that's a true set of equations or equation based on the block diagram. Now we want to take that into the time domain. And maybe before we take it into the time domain, we want to see these steps. Let's cross multiply and just make this one equation. Forget all these ratios. Let's just make this some polynomial in z relative to capital X sub I and relative to E. And we can do that by getting rid of the denominator or multiplying both sides by z minus 1. And if you had something that was not as trivial as a 1 in the numerator, that would just be doing a polynomial multiplication on E. But you now have a relationship in the frequency domain between this error signal E, Z transform, and this new variable, Z transform, capital X sub I. Or this is now Z, X sub I of Z minus X sub I of Z is equal to E of Z. Going back more steps than maybe you need to go, but I'm trying to return us back to what we've seen before. Now we should be able to very quickly take that into the time domain. We now have little x sub I of, let's say, L plus 1 equaling x sub I of L. So now I've pushed this minus x sub I, or I've added that to both sides and taken it into the time domain, plus E of L. Now we want to write the right-hand side in terms of state variable components and the input to our system. And E is not quite there yet, is it? But we know that signal E from the block diagram, that's actually right here, is made up of the output Y and the reference input R. It's just their difference. In the time domain then, E of L is just Y of L minus R of L. But Y is not in terms of states yet, is it? But Y is Hx of L minus R of L. We can use this expression for E in the x sub I equation to obtain the additional dynamics that we need to augment our system. Meaning, x sub I of L plus 1 is equal to x sub I of L plus H x sub L minus R of L. This was just our E of L. Where this first order difference equation represents the integral dynamics. Do you see, if somebody gave you a difference equation and it had x sub I on one side at time L plus 1, and on the right-hand side it had x sub I of L, do you see how that's integrating? That's just taking the previous x value and adding to it. And what's the weighting? What's our forgetting factor, or what's the coefficient on x sub I of L? It's not forgetting, is it? If it was 0.9, it would sort of be losing something. If it was 0.8, the next time step, it would have shrunk by 0.8 in terms of its influence on the next value of x. Now we're simply keeping all of that, and that's why we're integrating up, or x sub I represents sort of a building or an integration of the error in the system. What we want to do now is use this additional set of equations, it's just one, and augment, add that to what we started with, the original dynamics. So here we'll start with what we have for the integral dynamics. X sub I of L plus 1 is x sub I of L plus H x of L minus R of L. And our original dynamics, that's our original dynamics, phi x of L plus gamma U of L. We're going to use this. This is a bunch of dynamics. It's our Nevada dynamics with one more dimension added onto it. Let's now increase our state vector by 1. And then we will have our augmented system dynamics to design our Ks that we need. We need a K hat and a K sub I. Now I have a block matrix structure. How tall is this vector? That's our state vector, and we've been using different states. That was Nevada, wasn't it? It's n tall. How tall is this vector? We assumed we had one output and one reference input. That was just one. So now our state vector has grown by one. We're just augmenting it by one more component. We had Nevada components, we're just putting one on top of it. And if that's the case, then how big is this augmented system matrix that I'm going to call phi bar, capital Phi bar? How big is it? Or what does it look like geometrically? If you had to draw a geometric shape to describe phi bar, what shape would you draw? A square. What are the dimensions on that square? N plus 1 by n plus 1. And now, even though these may look the same, in my picture, these dashed pieces are of different dimensions, if that makes any sense. The lower right-hand corner, what's in that 2-2 submatrix entry of this phi bar? It's now x of L plus 1 is equal to something x sub I plus something x sub L. And I now need to go up to my equations right here and figure out what x at time L plus 1 equals. Does it involve x sub I as a component part? Is the right-hand side of x of L plus 1 contain x sub I of L? No. That submatrix 0 is dimensionally what? What size is that matrix of zeros? How tall is that? If you had to fill all these zeros in, how many zeros do you have? 1? Do you have 2? Do you have 3? Do you have 4? It has to be compatible with the rows in X, does it not? How many rows are in X? How big was our state? Which state was it? Nevada. It's n column or n rows tall. And how wide is it? How many columns? It's multiplying x sub I. How big was x sub I? So it's now an n by 1 submatrix. So I now have Nevada zeros stacked on top of each other. That's what that big 0 represents. What's here? The original system matrix. Do we need any other entries? Well, yes, we need to put in the U, and we don't need any R driving X. Can we now fill in the pieces for x sub I of L plus 1's dynamics? Do we have anything in the 1-1 submatrix? We have the identity matrix, don't we? And that identity matrix is how big? It's 1 by 1. So we just have a 1 right there. What do we have sitting off to the 1-2 submatrix? It's now H, isn't it? Because it has to inject X as if X was the output, and that's H times X. How much U is going into that? How much R? See, aren't we having fun? So now we know that this, all right, you didn't have to answer that so quickly. Now you have a phi bar and a gamma bar. And you can use that just like you had phi and gamma before, and you'll find a K matrix that's n plus 1 columns wide. You'll pull out n of those to give you the K hat, and one of those to give you the K sub I. This will all be on the final. Good luck. No. So if you go back, I just didn't want to tell you because I would have lost even more of the class. Although I lost 99% of you, I really appreciate the 1%. I've got an apple here that's paying attention. The 1% that paid attention, but you really are responsible for on the final about down to here. Be able to find this n sub 1 reference input gain, and that was maybe, what, in all of these? So down to C in terms of the state space matrix discussion. Open loop, behavior, behave, and tell us where to go. That's on the final. I will see you in a week, if not before, during office hours. Good luck on your finals.